And our first panel does not talk about asteroids technically, but we're going to talk about space medicine. And we have a real doctor with us in the room today, working at the hospital here in Luxembourg, the Hospital Robert Schuman. So we will welcome with us Felix Kleine-Borgmann on stage. Felix, oh, here you are. Thank you for being here with us. Let's give him a bit of round of applause. Listen. And so you have the next 40 minutes to tell us more with the experts that you gathered here for the Asteroid Day about space medicine. Thank you.
Thank you very much.
All right. Yes, should be on now.
Should be on. Thank you very much for the introduction. Yes, it's my pleasure to welcome you to our today's panel session on space medicine. As we probe deeper into space with extended missions on the International Space Station, eventually trips to the Moon and to the Mars, ensuring astronaut health becomes a challenge and also a catalyst for innovation, even down here on Earth. Joining us today are leading experts from the field of physiology, immunology, clinical research, engineering. I welcome you on stage. The panelists, come please and join me. We have Inês Antunes. She is human research lead and project scientific coordinator for the European Space Agency. We have Bothe, who is a clinician researcher at the Charité in Berlin, in Germany, working on the cardiovascular system and also on the circadian rhythm. We have Alexander Choukér, professor at the LMU in the Laboratory for Immunity and Stress, telling us today about his field of work. We have Bruno Santos, a developer and founder of Exobiosphere, a startup building a device for high-throughput orbital screening, a machine that enables us to work in space on cell culture and other experiments. And we have David Kim, a flight surgeon and physician for the astronauts, working as an emergency physician in Vancouver, Canada, and as a flight surgeon and primary care physician for the astronauts in Cologne with the European Space Agency. Welcome to the panel. And please maybe introduce yourself and what you do. Ladies first. Inês, do you want to say a few words?
Usually ladies first is to help ladies, not to be the first. So thank you very much for the introduction. So I work for the Human Exploration and Enabling Science Office, meaning that my focus is very much on performing and coordinating research that really addresses health of astronauts and that addresses the medical priorities of my colleagues, where also David Kim is part of. And we really work hard in trying to use our analogs and our space stations to really address all these issues and make the needed research. I work with a lot of strong science community across Europe, with doctors, with the MedOps people, and we really try to elaborate roadmaps that really address these issues, from radiation, decompression sickness, disorientation, lunar dust, all these priorities that are very important. We try to make use of our research to really find answers, develop countermeasures. And I have the pleasure to meet so much nice people, from astronauts, which are also the spotlight today, even though you got a low answer there, but please rest assured that I always have pleasure to be with many of you and work with many of you, and with the science community, with so many nice people in the European community and outside, our international partners. It's wonderful experience. So, and what I love the most is really for new ideas, new people, new challenges. So that's why I love being here today, because it's a new event for me, so I really feel honored to have been invited. Thank you so much.
Thank you, Inês. Bruno.
Is it working now? Okay. So, as I was saying, we co-founded a company named Exobiosphere. We are developing a device to enable mass adoption of pharma and biotech industry in space. The reason for that is there's actually a big problem on Earth that developing a medication costs over 2 billion euros, takes over 10 years, and still 90% of these drugs fail. And space has the potential to help on that regard and actually improve this process. However, doing this in space is extremely difficult. It comes with a lot of constraints, and we are trying to reduce these constraints to allow the technology to operate. So our ultimate goal is first, bring this innovation, find new solutions, get better, more effective drugs back to patients on Earth, but at the same time enable future deep exploration of space by having this device on board that allows for astronauts to get medication, to get diagnostics, to get what they need for actually keeping healthy and being able to take on these very long missions.
Thank you. David?
Hello everyone, my name is David. I have two jobs. My first job is working as an emergency physician specialist in Canada in Vancouver. And my second job is working as a flight surgeon for the European Space Agency. And that's where I get to take care of astronauts. You can sort of think of me as a private doctor for the astronauts. We do anywhere from the pre-flight phases, from astronaut selection, health maintenance prior to the flight, and also during their flight, supporting the missions to ensure that astronauts are healthy while they're in space. And after a space flight, to make sure that their rehabilitation and readaptation to life on Earth becomes normal and safe. And also, fourth little asterisk is also we talk about with our great team, how do we send astronauts and humans into deep space flight missions, back to the moon, and potentially one day to Mars and beyond. So that's some of my work that I do.
Thank you. Tom?
Yeah, hello, my name is Tom. I'm a physician and researcher from the Center for Space Medicine at the Charité in Berlin. And what I do is I try to go full circle. So I always start with an operational goal. For example, we need to go to Mars. We want to go to Mars and colonize the place. So this is basically what we want to do. And now we try to understand what are the requirements, what kind of technology, what kind of medical capability do we need to actually do that. And then we try to work first principle backwards. So what do we need to actually reach that? What kind of technology do we already have? Where do we need to improve? What kind of goals do we have to reach to actually get there? And so then we work together with a lot of medical industry to actually deliver some of the countermeasures, deliver some of the tools, evaluate them in space-like analogs, like parabolic flights. So to basically promote them, we have experiments on the ISS to see, do they actually help the astronauts? And then at the same time what we do is, because we as medical researchers, we always have to justify ourselves for why do you work in space? And that's very nice to the point that has been talked about earlier. It's like, why do we do this? And so what we do is try to go full circle, not only bring stuff into space, but try to use the technology that we developed there and bring it back to Earth. Because at the moment we have 5 or 6 astronauts, but we have 500, 600 million patients. And by going this full circle, and by innovating into space, but also innovating out of space back to clinics, and back into medical industry, we try to really close the gap and bring together two fields which in my mind are very much connected, but in the public and also in the industry reception often not yet. So this is why something like this is very, very helpful. I'm very grateful to be here, and I'm very happy to join the panel today.
Thank you very much. And Alexander?
Yeah, it's working. Alexander Choukér, I'm a physician, I'm an anesthetologist at the University Hospital of Munich, and I've started kind of 25 years ago to use space, so to say, to find out what is the difference between someone who's lying in bed and who is sick, a patient in the intensive care unit, and the other case, what are space, how to say, travelers preparing themselves to or simulating space while lying in bed, while they are very healthy. So this was the entry, and this has followed up in the last 25 years, always with the question, how much knowledge, technology, and added value can we leverage out of this interaction between space and Earth, and the problems that we have here in patients' care, and also conditions that we can only simulate in Earth analog environments. We will talk about this later, related to spaceflight. So this is a translation between clinical and space research. This is the field I'm working in, and I'm very happy to have this forum today with all together, and thank you for the invitation and the Asteroid Foundation for having organized all this, because this is exactly what we need to say and to state. This is not only, the research in space is not only for 6 high performers, so to say, who are going far out, but it's really for them, of course, as well. But there's a lot of reflection back to Earth, and we can take advantage of these of this knowledge and technological developments. Thank you.
Thank you very much. Well, when astronauts are shot into space, they encounter a vastly different environment from Earth. I'm thinking, for example, the most obvious, gravity, which has changed. It's still there, but there's microgravity. It's mostly countered by speed. But there's also radiation. There's also a vastly changed circadian rhythm. Our day-night cycle changes at the speed at which the space station goes. A day only takes 90 minutes. So what are the immediate effects the astronauts notice when they go up, and what are the most crucial challenges at first? David, maybe you could start with that.
Sure, this is a great question. So when we think about space, space is actually trying to kill you. It's not made for humans to survive. We as humans have evolved to survive on Earth, where there is an atmosphere, where we have oxygen and air to breathe, and pressure to sustain our bodies, and we also have gravity. And when we go to space, we have what we call the 5 hazards of spaceflight. Radiation is one of them. The second is the hostile environment, as I was talking about, without oxygen, the temperature variations, etc. It's the closed and isolation environments. There's microgravity, which affects a lot of changes in our body. And then the 5th is distance from Earth, where that means you don't have definitive medical care if something happens, and there may be communication delays and lack of evacuation options if there's a medical emergency. And when we talk about what happens to our bodies in space, I would say one of the first things that astronauts may notice is space adaptation sickness, and we can probably ask our astronauts in here in the room, but typically with the change in the visual cues and changes to your body in the microgravity environment, people experience dizziness, sometimes nausea, a bit of vomiting as the first sort of adaptations in space because of the change in your sensory system, as well as fluid shifts in your body. So you get an immediate fluid redistribution to the head. So what we call bird legs and puffy face syndrome, where your head gets a little bit larger and your legs become a little bit skinnier. And those are some of the interesting changes that happen to your body. And what we work on is to ensure that the systems on board the ISS and systems for deep space flight ensure that we create an environment that's survivable. Because really, the limiting factor in space travel is humans. We've sent probes millions of miles away from Earth, but we haven't gone that far as a human species beyond the lunar orbit, for example. So I think humans are the limiting factor when it comes to human spaceflight.
Puffy face and bird legs, fluid shift, increased intracranial pressure and blood pressure. Those are physiological changes that are very interesting and hard to account for. Tom, how does that work? How do you find out what happens in the body and how to counter that? Is there anything we can find out and do about it?
Yeah, there's a lot. There actually is a lot to find out. And the funny thing about the fluid shift is it's not that difficult to detect because you can see that. And you all can do an experiment. You can look at the 2 astronauts here, and you can look up a picture, maybe find one from space, from the first days of the space flight. And you'll see the puffy face. This is not just a funny description, you really can see that. And we do some experiments in parabolic flights, and you even see that instantaneously. So only when you have 22 seconds of micro-G, you'll see the puffy face immediately. This is just fluids coming up. And well, as you said, this is, well, first descriptive, but there's a lot of physiology behind that creates problems. So another big issue we have on the ISS is there's basically no wind, right? And so a lot of the body temperature regulation that we have here, well, you can use different clothes, you can seek shade, you can regulate the temperature, but also you're very dependent on convection, so basically on wind, airflow, transporting energy away. Now what happens if you have a fluid shift up into your head? So you pump more fluids in your head that isolate it thermally and you have no convection. Well, your temperature goes up and you get space fever. And we are right now working on a project where we see, well, it's literally only in the head, the space fever. So the further you go down, the less of that you get. When you get down to the lower extremities, you get the inverse. You get a cool down effect. And this is a lot of follow-up effects that then follow not in the immediate first days of spaceflight, but they come after months, maybe even after years. Like there's so many compound effects. And so the question you ask is exactly right. How do we study that and how do we find countermeasures? And this is quite difficult because we only have a very limited amount of astronauts and they are so time constrained that we can't just try out random things on them. So we basically have to, and maybe Inês is the right person to answer the next question, is like, how do you start from something that we can do in the laboratory, just using a tilt table, using a table where you lay somebody down, you flip them up and down, you measure physiological changes, to going to centrifuge experiments, to going to bed rest studies, to going to parabolic flights, to basically have this huge pool of ideas, narrow it down to one or two very, very good ones, you think good ones, and then trying to get it into human spaceflight, and then validating that. So there's a very, very long thought process there, and it's, I think, to me, the most amazing part of how we do research is because we have a lot of ideas, but having a lot of ideas is very easy. Having one or two good ones and finding them is very hard, and I think this is operationally for us the hardest thing to do.
Inês, how does it work? How do you decide which projects to take on, which data to collect from the astronauts, which parameters to measure when they are up there? Who brings the ideas and who decides what to do?
Yeah, so when there is opportunities for example, space stations, we of course release an announcement of opportunities in ESA and with priorities. So if we have missions to space, we open the calls to the community, but we do really highlight priorities, you know, being priorities in exercise, muscle use, muscle disuse, bone loss, but also, like, of course, all these problems of decompression sickness, fluid shifts, SANS, etc. So, and we ask the community to submit proposals that address those priorities, and the best priorities, they are evaluated from a scientific merit, but also from relevance, feasibility, if they really address the problems we have, and we communicate more with the medical colleagues to really understand and accommodate these experiments or even adapt them to really focus on those issues. But in addition, we don't work with astronauts only, as you said. We also, because ISS, for example, which is the station we have been using so far for several years, more than 2 decades, it's wonderful. It gives you all the space conditions that one can have in LEO, in low Earth orbit. It gives you the radiation of LEO. It gives you microgravity, isolation, confinement, all these conditions. Together, we cannot separate them. But, of course, we have to share the station with a lot of partners. There are only a handful, or now 2 handful of astronauts. They are working for us 8 hours a day, sometimes even more, for everyone, for all the experiments from JAXA, NASA, Russia, Europe, NASA. So we cannot do everything there. Also, communications is of course is more difficult. What you can do there, operational, what you can bring there and bring down. So we have to rely on ground analogs as well that allow us to do more statistical power, but also it allows us to isolate these conditions. And in fluid shift, we do conduct bed rest studies. For the ones that are unfamiliar, bed rest studies is where participants stay in a bed, slightly with a head down tilt of 6 degrees, because then not only they stay in the bed for long periods of time so that you can simulate muscle and bone disuse, but also to really increase that fluid shift that needs to happen for us to do research. We also do announcement of opportunities. We also put and set priorities for those research, including the effects of fluid shifts, but also at all other areas of cardiovascular, bone, muscle, etc. And with this announcement of opportunities, we really receive really great proposals from the scientific community all over the world. Even if we are ESA, like there is a lot of groups of scientists that collaborate from all over the world, and we do great science to address those issues. So this is how we work. So we try to provide as many platforms as we can. and bed rest is one of them. Of course, we have others that I can elaborate further, but not now. But yes, that's how it works.
So a mixture of analog studies and a careful selection of the precious astronaut time. I think we will come in a second to how precious this astronaut time actually is. Before, I want to mention there's not just the fluid shift, but also the immune system is massively affected, and even the astronauts with their nerves of steel, as they probably are, otherwise they wouldn't sit on top of those rockets. They experience an increase in their cortisol levels, both during start and during landing, and then they are subjected to a whole lot of different stresses. As David already said, there's confinement, there's isolated space, there's radiation going onto the body, and that is a massive challenge also for the immune system. And Alexander, can you tell us a little bit on what that does to the body and to the astronauts?
Thank you very much. I mean, this was a great introduction as well to the topic, and from you and Inês. I think what we have already, before starting to go into some details, I mean, the importance is here in space research. There's a big advantage. We have to look on the whole organism as such. Yeah? Not only everyone of course has the expertise, but we have to integrate all this knowledge, because the influential factors, as you stated in the beginning, are so various and so unique, which is a real advantage, and which makes maybe this community also probably the most friendly scientific community, because we all have one goal and we all can contribute to this goal, to understand how the organism is behaving in these extreme environments and which organs are affected. Yeah? In my case, of course, as you said, immunology is our field in our laboratory, and they're linked to the changes of the immune system towards the challenges you are faced to. Yeah? And you can just, when you look back into our evolution, our immune system has evolved with the challenges we have had. Yeah? Since it's like a muscle, when you don't train it, it will not grow. Yeah? So you have to grow the immune system by challenges, which started from a single cell now to a very complex organism as we are, living in a very complex environment, which means a lot of checks and balances have to occur in the body. And those are sometimes when you are in extreme conditions, so when the system gets out of balance, leading to diseases. Yeah? There are some good indications regarding maybe vaccination successes when you're very stressed, and so the vaccination success is less. When everyone knows it from himself, when he has encountered very serious periods of load, he's getting sick. Not to our surprise, of course. When you look on humans who are super trained like astronauts, or also expeditioners going to the Antarctic, really performers, I would say, you can investigate, though, the shift of the immune system under these extreme conditions, which may result, for instance, to viruses that you have in your body that are replicating, yeah, that are no more under control. You have imbalances of your immune response, which may lead to allergies, for instance, and rashes and things like that. Not in everyone, but in many. And this depends also on the load that you put on these individuals. And we did also some observational studies. When you look back to the history of different isolation or analog environments, the more the load is added to this subject, so duration, severity, like Antarctic, being 1 year in hypoxia and so on, in high altitude deployed, this adds to this immune disbalance gradually. Yeah? And space is one of the harshest environments, so it's very interesting to research that, to see how it's imbalanced, getting imbalanced, and how to rebalance it, because it takes quite a while until we are back to normal. So it's a very unique field of research and research opportunities which are offered by the space environment. So I can only encourage everyone, the younger people, to engage in this field, because it offers so many opportunities. Yeah, thank you.
Thank you. We definitely need to come back to that in a minute again. The research on the space station is a very scarce resource, obviously. I was told that a minute that you want to spend, the astronauts doing an experiment, costs as much as 2,000 euros that the project sponsor has to come up with. You found a way to do experiments on the immune system, for example, but also on other systems, in a semi-automated way, including microscopy, cell culture handling, and everything. Bruno, how does that work?
So we took a bit the approach I do on Earth. It's basically you understand for a macro perspective how it's work on the human body. We understand what are the molecular reasons behind this happening. And then we try to model these effects in a Petri dish, and then we test on this Petri dish. Of course, you cannot do an experimentation directly in human bodies, so this is usually the strategy that everyone is using on Earth to be able to develop new medications, understand the disease, etc. So here on Earth, we don't have any constraints, so we have large automations, we have big machines, we can test millions of potential drugs to solve that issue. However, when you go into space, the weight that we bring to space, the cost, astronaut time is limited, then standardization of process is very important in these kind of systems because cells are extremely sensitive. A minor shift can cause a negative to a positive shift, and then you don't trust really the results. So we wanted to bridge this gap and actually be able to represent all these features that are being described here, from muscle generation. There's effects of accelerated aging on astronauts that luckily they are somehow reversible at some point, but there's this accelerated aging at the molecular level. And we wanted to represent this in a Petri dish, in a plate, and test medication in space, in the same environment that the astronauts are living, and try to see if you can avoid these effects to happen or even reverse them with medication. So we developed this platform to do exactly that. In one small box, the size of a carry-on suitcase for the plane, we can test over 2,000 conditions already, 2,000 compounds. And in the future we'll scale, and we'll be able to do over 300,000 per run. But that's the starting point, and that's the way you see for in the future be able, first in deep space exploration, once more, is like astronauts don't have access to any new medication, so they may have to produce it themselves, because just coming back to Earth can take over a year. So they need to have solutions on site, immediate. So this is a platform that can be used not only now for developing new medicine to bring back to Earth, but in the future as well to be used on board by the astronauts and find like life-saving treatments on the spot.
I hear recently there was a development of a drug against the difficult-to-treat triple-negative breast cancer. Why did it need microgravity in order to find the solution and the access point for this treatment?
Very interesting question. So there's a scientist, Dr. Katriona Jameson from US, and they sent triple-negative breast cancer to space. This is a type of cancer that is known for being very difficult to treat, one of the most aggressive, life-threatening. And to do research on these cells on Earth, sometimes some of the effects they saw in 10 days in space, it'll take them almost 10 years to do on Earth. You see how dramatic this difference was. So in only 3 missions, they were able to identify a new molecular target for this type of cancer, developed a new therapy against it, so discover a specific drug that works against it. On the second mission, validate, and is actually right now in clinical trials and having very promising results.
Very interesting. Inês, yeah?
I actually would like to add that pharma research is very important because, as you said, the more we move beyond LEO, we will need more autonomy. We will need diagnose systems that really support the crew to take decisions because they will probably have less support from flight surgeons because of communication delays. Also, what we can bring up and down, it's very limited, so we need to develop systems and provide the resources for them to treat themselves if there is a situation. And pharma research is very important, not only if we can produce it in flight, because sometimes we need to be prepared to produce anything according to what we need, but also we need to understand pharmacokinetics and pharmacodynamics, which is if we fly a pharmaceutical, does it change when it's in space? And does it degrade? Because of course you have radiation, you have all these microgravity, these impact the pharma. But also if it changes when the astronaut takes it, how does it is working on our system, and if it does what it's supposed to do. So I really find very interesting this research, and I think we really need it more and more, because this is the future. If we want to go to Mars, we need this kind of research urgently. And another thing I wanted to say, because also you touched base on that, is like, astronauts are really good models even for research on ground, and maybe Alex, you can corroborate what I say, because they go healthy and they age faster, so, and they return, so they are not sick when they go. So we can actually study aspects of aging on astronauts from a point where before they flew, what it changed in flight and how they returned. Because on ground, you deal with sickness. You don't have access to data before the people were sick. So this is really interesting. Astronauts are also very good models for that in all types of research. And I just wanted to say that because you touched base on those, and I think it was interesting to mention. Well, thank you.
Yes, that's indeed true. I hear there were also recently twin studies on astronauts and their counterparts on Earth, and you could see quite some differences and insights from there. Any comment on that from the clinical researchers, maybe?
Yeah, happy to. I mean, thank you, Inês, for pointing to the aging processes. I mean, this was at the beginning quite of kind of surprise that, you know, we saw it first in the bones. Yeah, this was the first indication. Then in the vessels, then in the immune system, then maybe in the brain. And so other organ systems or the muscle seem to be affected like in aging populations. And very recent data and knowledge also regarding our field, that I'm involved in inflammation, links this kind of this kind of increase of an inflammatory state of your body in space, for instance, which is called inflammaging, which means that you have an increased level of activity of a certain part of your immune system. And this was a very interesting observation in the crew members and so on, but it's now linked as well on Earth. This inflammation in the elderly is, so to say, the trigger or the cause. No one really knows for many diseases of the elderly. So this might be really linked to the different organ systems. We have to find out, and I think the advantage of this community is that everyone is quite open to share data, of course, not of confidential nature, but research data to get to a picture which is a little bit bigger than you would ever find out when you work in normal environments, because there's a certain goal to achieve. Yeah.
I might want to add like a different perspective, sort of a different perspective on that. You said we have twin studies, which is very, very interesting. But that is very interesting when you look at, for example, genetic things, when you look at aging, when you look at very in-person stuff or intra-person stuff. But we can use astronauts as perfect lab rat models for some things that are super, super important on Earth, but that we just can't study. I'll give you a very simple example. Just imagine you have somebody who has a motorcycle accident, who has a massive bleed, loses 1 or 2 or 3 liters, and you come there as an emergency doctor. Well, you have your best standard of care and you know exactly what to do, and you can only do that. Now, when you have an astronaut who flew in space, because there's no gravity, all the blood goes up into the central circulation system, and that system adapts to that, especially over long duration missions. And when those astronauts come back to space, they come back from space down to Earth, you have gravity again, and all the blood flows back down into the legs. That's about 2 to 3 liters of blood initially that pool. Physiologically, for that, what happens to your central circulation, that's more or less the same thing. Now, the thing with the astronaut as well, if you try to stand them up, and there's quite interesting videos of people where they basically drag them to have an interview immediately after landing, well, some of them actually faint, and you can ask the astronaut colleagues here, that's not quite easy to perform. Well, but if they don't feel great, you just lay them down flat and they're okay again. With the patient after an accident, you can't do that. But what that means is now with the astronauts, we can try out our countermeasures. We can try out the things that we can do to help them. And if that works in the astronaut, it will also work in a clinical patient. And I think this is the opportunity space that we all work in. So there's so many fields of intersection where there's massive opportunities for improvement in medicine, but also for commercial success. Just imagine you have a device like that. That's a massive commercial opportunity, and I think our job now is, and I think this is where we have not been optimal over the last decades, is to really to give you that information, to tell you about all the opportunity spaces that we have and where all the intersections are, because we can't do what we want to do without the support from the agencies, but also without the support from the public and from the companies to really help us to get there. And so, yes, the astronauts are very, very important. And so this is why we all hope to get more astronauts in the future and not less. And so please talk to your local politicians to make that happen in the future.
The data from astronauts is really valuable, as we hear. How does it work with the astronauts? How do they pick their projects that they take part in? And how much of their health data do they actually share? I mean, I know there is a patient-physician privilege. I hope I'm not breaking it when I'm saying that you're now preparing Sophie Adeno for her flight and also in picking out her projects, and you're doing the pre-analysis. How much can she share? How much can you share? How much will the scientific community contribute or profit from that?
No, this is a really great question. So when astronauts become the test subjects for various scientific experiments, what usually happens is we have a big meeting and we come together as the flight surgeons and the crew, and all of the science experiments that are proposed is presented to the astronauts. We talk about the risks and the benefits of the science experiments, what kind of tests might be required, anything from CT scans to blood draws and post-flight data collection. But ultimately what it comes down to is we advise the astronauts the risks and the benefits, but ultimately it's the astronauts' decision on which studies that they will select. So they get a piece of paper at the end of these, what we call the informed consent briefings, and then they'll decide, I want to do this study, I don't want to do this study, I'll do this study and this study. So that's sort of how the consent process works. We provide the medical information as to the risks and benefits, and ultimately it's the decision of the astronauts, which is pretty cool.
Thank you. That's indeed cool. It seems that when astronauts go to space, the adaptation to space itself, once you went through the phase of space sickness, is fairly easy. But when they come down again, readaptation to gravity is another aspect of the whole story. What are the challenges there, and how well does it work for the astronauts who are really healthy normally, but when we now bring in tourists who are maybe not as carefully screened, when we do longer duration flights, the readaptation to Earth and maybe also the adaptation to other orbital bodies around the sun, what's the challenge there, and how well does it work from the experience we already have? To all the panelists, maybe.
I unfortunately, as a representative of the science community, we have very much focus on the science we want to perform post-flight. So the first week after flight is very important, and then later, but still early. So I think during that initial post-flight phase, the astronauts are very much absorbed yet still in a mission. So we don't have so much long-term feedback on how they feel on a personal life, and I think that maybe falls on the medical area. But I do know that, for example, we do isolation studies and confinement studies, and I do know, I have talked, one of our isolation and confinement analog is Concordia in Antarctica. So basically this is an Italian and French station where we just piggyback on the crew there. They do research on glaciology, climate, and they maintain the station, and we asked the platform owners if we could do research on this crew. And one of the things that I have asked and that I have noticed from many of the crew that comes back, especially the ESA medical doctor that we send there to perform the experiments, is that these people, they come to a new world afterwards. It's like they didn't buy anything during the mission. They had no access to their credit cards and accounts. They only communicated to their family via distance, and they were used to be together for a year or 6 months, even for astronauts. They were together and they had created bonds. So when they come back, they are really like, oh, they are really shocked, like, my God, so much is needed from me, and I have to keep up with these, and these people all want to be with me, and I don't want to. I don't want to. Some people even tell me, I need time, please, let me be. I want to see my crew again. Where are they? Some people told me that, and it's interesting because it really shows that you create a lot of bonds with your crew member, and that's very important. When you go to space, you want a mission success, so team dynamics is very important. Psychology state, it's very important. And it's not just about doing the mission, but it's about also living the mission, and living that mission comes with a lot of experiences, and when you come back and it's over, it's like you belong to another world, and I want to come back. I want to come back to space, or I want to come back there. So this is more or less the feeling I have had when I talked with people from Concordia, from more the psychological standpoint. I do know that some of them come with some disorientation and have some car accident when driving, right? But that's more for space, and that's also a priority. But yeah, that's the experience I have heard. And also, just to touch base on something that Alexander brought up, is that, of course, the immune system is also affected, and the mission brings stress. So sometimes they also come with kind of intolerances, right, or allergies that they develop because of stress, which it's new, so it's kind of demanding, but also very rewarding, I would say. And the truth is that when we talk with astronauts, they always want to fly again. So
I think that is a great part for an overlay for the later astronaut sessions, where we can learn from their experiences directly, and I'm sure we will get the chance to ask them about that. I fear that our time is already running out. Maybe we have a chance to take a question from the audience still, or two, if any comes up.
Okay, I can take that one. We're actually considering to implementing CRISPR screening in our system at a later point. Not directly on astronauts, of course. That's more, well, I would not say it would be suitable for that. But for testing genetic reasons for some feature that you see on the disease, and to see if we shut down one gene, we can get this disease somehow under control. This is something we are implementing. Of course, this will then be translated some kind of like drug target that will have a similar effect on it, but will allow us to better understand the disease and the molecular mechanism behind.
I feel that the CRISPR system is basically like a pacemaker for evolution, because it's doing the same thing that you would also see happening with natural variation. And maybe that's an interesting point, because you would use it, if you wanted to use it, in order to react to additional pressures of evolution. And maybe that is something that we will actually be seeing as we move into space, that we create different evolutionary pressure points. As when life left the sea, it had to deal with whatever happened on land. As life became more abundant, it had to deal with the surrounding and with other living organisms. And now we move in space, and we maybe see different pressures. For now, we only send middle-aged people up there. It would be very interesting to see how juvenile bodies react, also especially with regard to the immune system, that is an adaptive system. Maybe we could see interesting things evolving there once we establish colonies in space, right?
I'm sorry, I think we need to come to an end, unfortunately, although the discussion was very interesting. Thank you very much. We can give them a round of applause. Yes, feel free to leave your masks here. And thank you again, Felix, for gathering all of these space medicine experts in Luxembourg and to give us the chance to have this conversation. If you'd like to ask follow-up questions, I'm guessing you'll be around as well throughout the festival, right?
Yes, we will be outside, and you can find us and directly approach us naturally.
Thank
would
you
be
very
very
much,
happy about
Felix. Thank you.
Thank you as well.